So what we're going to do today is we're going to start talking about various patterns that are associated with different binder mechanisms, different AIDL mechanisms, different bound and unbound services. If you recall, we talked about the command processor pattern in the context of started services, and now we're going to start talking about some of the other patterns associated with both started services as well as with bound services. The first pattern we're going to talk about is a pattern called the Activator pattern. And as you'll see, this pattern appears in a couple of places. It appears in a paper that I wrote that has appeared in a couple of different venues over the years that I was a co-author on. And a small snippet of this particular pattern appears in the POSA 4 book. When we redo the POSA 2 book next summer, this pattern will appear as a full-blown pattern in the POSA 2 book. So here's the context of this pattern. It's often the case when you're building software that you run in a resource-constrained environment where it's not necessarily appropriate to pre-allocate a lot of resources. For example, in many smartphone environments, random access memory, RAM, is a fairly precious commodity. And even though we've got a lot of memory now in Android and iPhone, you never can have enough. So you have to be careful to over-allocate this stuff. In older versions of Android, particularly, they were much more memory constrained. They only had, hundreds of megabytes, not gigabytes worth of memory back in those days. And so as a result, it was even more important to think carefully about how many resources were available. The problem, of course, is if you're in a memory constrained environment, it's not really appropriate to have all your services running all the time if they're not actually being accessed by the clients. Because if they're running and nobody's using them, then you're chewing up resources. And if resources are precious, in other words, you don't have a large amount of them, then when someone comes along to run the next application and there's already a bunch of services that are taking up memory, but they're not being used, then the next service to be launched may very well fail, even though there's plenty of available space if you were to reclaim the stuff that isn't being accessed on a regular basis. So you can see here we have a couple of different services that are running, and when the next service comes along, there's not enough room, even though they're not all being accessed at the same time. There's more discussion about memory management on Android here at this particular link, and there's specifically some discussions about services that we'll talk about in a second. So what's the solution to this particular problem? Well, it turns out to be pretty straightforward, and it's something that Android does. It's something that a lot of environments do. A lot of middleware does this kind of stuff. A lot of network programming toolkits and environments do this kind of thing. It's something called the Activator pattern, and it's used to activate and deactivate services on demand. So basically, if you have a service to do work, don't bother running it if there's nobody there to access it. And that's pretty much how the Android services work, if you think about it. Started services get started when someone invokes start service and passes in an intent. Bound services get started the first time they're accessed, and they run as long as a client has a binding to them, and once that binding goes away, they evaporate into thin air. Naturally, somebody, either you or the middleware, has to be responsible for keeping track of these services to make sure that they get shut down appropriately so they don't end up leaking resources when nobody's using them, or you don't end up keeping them around and leaking resources and doing silly things that make it difficult to reclaim the memory. And we'll go through this particular diagram a little bit more detail later. As you can see here, basically what happens in Android is whenever you invoke bind service, be it a started service or a bound service, it'll go ahead and check to see if the service is running. And if it's not, and it does this by talking to something called the Activity Manager service. And the Activity Manager service plays the role of the activator, and it's got some other stuff we'll talk about shortly. And what it does is it goes out and checks to see if there's a process running that is running this service already. If so, it goes ahead and basically says, you're it, do your thing. If it's not the one, if there's not one running, it goes ahead and starts it up. And then at some point later, say we're doing a two-way communication with AIDL on the binder, then when an invocation takes place, it gets routed to the service that's up and running at that point. But Android has started that service on demand. And there's some more information here at this URL that talks about how to manage service life cycles appropriately in Android to conserve memory. Now, as is always the case when we start talking about these kinds of arrangements of software. This is not just a random collection of classes put there for some arbitrary reason. There's some thinking that went behind it, and that thinking is something that's been documented in the literature called the Activator pattern. And the Activator pattern's intent is essentially to automate the scalable on-demand activation and deactivation of service execution contexts, which is just a fancy name that means a process, a thread, a container, or something, to run services that are accessed by clients without requiring the consumption of excessive resources, because things aren't actually running unless they're used. So you take a look at this link, you'll get a paper that talks about Activator, and as I said, there's other places to learn more about it. So when would you apply this pattern? Well, you typically apply this pattern in situations where you have services in a system that really don't need to run unless somebody is actually accessing them at that particular time. Now, here's an interesting question, and we'll talk about this a little bit later when we get to the consequences section. But is it the case that every service is such that you can start it on demand, or are there some services that may need to be pre-started? Does anybody have any thoughts about that? Why wouldn't you just always launch things on demand? What would be a reason for that?
They take a long time to launch.
If they take a long time to launch, right? Some things take a while to start up. Back in the sort of the bad old days of Java, before people did lots of clever optimizations to the VMs and so on, when you first started a Java application, it took a while to run because it had to load in all the classes in the class library, and that took a while. And imagine what would happen if you wanted to launch an application on your Android phone and you pushed an icon and you had to wait for 5 seconds for the thing to load, right? You'd be pretty frustrated. So clearly, some things have to be able to be ready to go, hit the ground running. People have solved that problem by various ways. Typically, the trick is either to load things partially so they start up and then they load incrementally, or to preload some things from the beginning. What are some other reasons why you might want to not have things launched on demand? So starting up, and it's all related to the idea of taking too long to start. So certain kinds of real-time operations where you're sampling the temperature of the nuclear reactor core, you probably want to make sure that you have very high accuracy, or you're checking some condition in your anti-lock braking system to see whether your car is skidding or something like that. You don't want to sit there and launch these services on demand. They've got to be up and running because they may be part of the safety critical or mission critical part. So the point of this is that this pattern is not always applicable. It's applicable when there's situations where you only need to consume resources if somebody's actually using you. And also if the client can benefit from being shielded from where services are located, how they're deployed, when they're deployed, how their life cycle is managed. In other words, we can decouple the client from some of these bookkeeping life cycle kinds of issues. And sometimes that's possible, and sometimes it's not. So you have to kind of decide in your environment what's the appropriate consideration about latency of startup time, reaction time, and so on. And we'll talk more about that a little bit further along. So here's a view of the structure and participants of this pattern. And there's a lot of pieces, but they're all fairly straightforward. So especially in their mapping onto Android. So there's a client, and the client's whomever is going to do something that requires a service to run. So in our environment, that would be like an activity that wants to start a service by start service or bind service. And then we have some way of identifying a service. And there's lots and lots of different ways to identify services. If, for example, if we were programming some kind of internet application, we would probably identify the service by some combination of IP address or host name and a port number. That's how we might identify a service. So the FTP service is at port 21, and so on. The HTTP service is at port 80, and so on. In the case of Android, we identify services by intents. And we either do it through explicit intents, where we say, please go run this particular .class file, or we do it through so-called implicit intents, where we say, here's an action I want you to perform, or here's some data. Go find someone who knows how to launch a URL that starts with maps.google.com. Right? You can do it different ways. That's how you identify services. There's then something called the service proxy, which is what the client sees in order to be able to do an operation that will eventually cause a service to start up and run. And in Android, that's typically done by the context, right? So you have operations like bind service or start service, which are done through the service proxy, which is the proxy, the context information. Then you have the activator itself. The activator itself is really this agent that interposes itself between the client who wants work done and the service that wants the work to be done. Think of the activator as sort of like a Hollywood Moogle, whose job it is to connect producers with movie stars, right? You don't necessarily call the movie stars directly. You call their agent. Think about, sports stars. You don't call the person directly, you call their agent, right? So there's this intermediary role. That's the activator. And the activator makes use of something called the activation table. And the activation table keeps track of who's out there that's actually up and running to be able to handle the new request that came in from the client. And then we have something called the service execution process. Oh, and the activation table in Android, for what we're talking about, is something that's part of the activity manager service called the service map. And the activator in this case is the activity manager, or activity manager service. And then we have the service execution context. That's where the actual work gets done, or that's the context in which the work gets done. In the case of Android, that's a Linux process, or more precisely a thread within a Linux process, but it's something that's managed by the underlying operating system. And then finally, we have the service itself that does work on the behalf of whomever. And so an example of this would be some subclass or some implementation intent service that's actually going to do the work. So that's a nice quick mapping of the contents of the pattern onto all the various mechanisms that Android provides in order to carry that out. And what's so cool about this is it's really not a stretch at all. I mean, these are all fairly straightforward mappings of Android classes, Android mechanisms directly onto the things that are in the pattern. But the pattern was written, many years before Android was even a glimpse in someone's eye, showing once again the generality of patterns. Here's an interaction diagram that kind of shows the dynamic communication between the different roles and responsibilities here. The client starts out by invoking an operation, and perhaps unbeknownst to the client, perhaps beknownst to the client, there's an activator that's actually interposed between the client's request and the actual service that gets run. In the case of Android, it's kind of obvious that there's somebody going in there because you call start service or you call bind service. So that it's kind of makes it clear that somebody's doing something to get things running. In other environments, such as internet application development, where you're connecting to port 80 or to port 21 or whatnot, it's not quite so obvious that there's somebody getting involved as an intermediary. And yet other middleware like Corba, as we'll talk about in a second, it's totally hidden from you that there's some intermediary that's getting involved. So the degree to which the client actually knows about this might or might not be directly visible to the application programmer, but the middleware knows what's going on. When incoming requests arrive, the activator actually handles them, and it goes and it checks, it looks up in its activation map or table and says, hey, is there somebody here who's already handling this thing? If so, I'll just route it to them. Otherwise, I'll have to go ahead and activate the service execution context. So that might involve forking a process or spawning a thread or loading a container. There's a couple different ways to do this type of thing. The activator also can decide what the granularity is it wants to activate and passivate things. So it might, for example, as is the case with start service, it might go ahead and launch the service every time start service is called. You call start service and it's probably going to launch something on your behalf. Conversely, with things like bound services, it'll launch it the first time, and then a bunch of methods can be made back and forth, and as long as the client hasn't gone away, or as long as there's some client that maintains a binding to the service, then the service will remain running. So there's this granularity issue. Do you launch things on a per method call basis? Do you do it on a per binding or connection basis? And there's no one right answer. Just the pattern gives you different trade-offs between different forces of fine-grained versus coarse-grained launching of activities. The activation table is actually what keeps track of all this stuff. It's implemented in Android, as you'll see, as a map or several maps, a couple of different hash maps. And then finally, we actually have the service itself, which is the thing that does the work. In Android, that really is something called a service. In other environments, it could be a function call, or a procedure call, or a method call, or something that gets run in response to an invocation by a client. So that's kind of a quick tour through the pattern. Let's talk a little bit about the consequences. What we're going to do here is we're going to come back later, next class, and talk about the implementation details of this. And I'll kind of neck down into how Android implements some of these things. So for right now, we'll just kind of talk about the consequences. So some good things about Activator. It utilizes resources more effectively from the point of view of not allocating stuff that isn't actually being accessed by a client at that particular point in time. So you're launching things on demand rather than having to pre-spawn them and keep them around. Another thing you get from this is sort of a coarse-grained concurrency. So you're launching processes, you're launching threads, and those guys are able to run. And if you've got a multi-core machine, if you've got an operating system, a middleware that supports concurrency and parallelism, then you're actually running those things at the same time. But it's a fairly coarse-grained approach. It's typically not at the finer level granularity of threads. It's usually typically more at the level of processes. And of course, the minute you start building your system out of pieces that are more service-oriented, more modular, then certain things get easier. Testing becomes easier because maybe you can test these things in isolation. You can also perhaps be able to reuse stuff. It's easier to understand because you're not building a gigantic system with lots of pieces that are all wound together like a big ball of mud or a big ball of spaghetti, but instead they're more modularized. So this allows you to think about things in isolation. So those are some of the benefits. There are some downsides. One of the downsides is the fact that the system becomes somewhat less deterministic. So sort of when stuff starts to run depends on the order in which clients make requests. So your system may not always have the same resource utilization. Sometimes it may take more memory, sometimes it may take less. Depends on the load. So that's why certain kinds of real-time systems tend not to use Activator because they don't want non-determinism. They want to know what's the worst case execution time, what's the worst case utilization of memory, so we can pre-allocate those resources and make sure that we always have enough. Whereas some systems say, you know, if we get a big burst of load, it'll slow down for a while till the load gets done, and then we'll kind of back out and go back to normal processing. Some other tricky things, because you're spawning things dynamically, there's potentially issues for security. If you're not careful, someone might slip in a Trojan horse so that when something gets spawned dynamically, rather than spawning the official version of a service, it might actually end up spawning some other sort of malicious version of the service. It might be a Trojan horse. It might have some malware or some other bad behavior. And that's just a little easier. The more dynamism you give into your system, the easier it becomes for people to slip in Trojan horses and backdoors without people really noticing what's going on. The other thing, of course, is when you start spawning things dynamically, you often don't know what your system's going to do until it runs. And there may be some subtleties about interactions between different services that will cause problems if they happen to get spawned in a particular order at a particular time. So this is the feature interaction effect problem. And so things may work fine when you test them in isolation in the lab, but when you combine them all together into the final integrated system and you start spawning them and they're coming up and going down and so on, you may have some surprises. There's all kinds of subtleties that go on there. And of course, the other issue is the whole issue of just there's more stuff going on. You've got to have this extra Activator thing that sits around. You have to configure it somehow. You have to manage it. You have to know how to use it. And so people have to learn a few more pieces of the puzzle. And so it's not always as easy as just starting a service manually. You may have to register it with some kind of daemon or some kind of manager that keeps track of this stuff for you. So there's a number of interesting known uses. One of the earlier known uses of this particular pattern is something that system administrators are well versed in these days, but end users are typically not really aware of. And it's something called inetd, which is often referred to as the Internet Super Server. And the Internet Super Server provides two different kinds of services. One kind of service is internal services that are linked in statically when the system starts, like on a server that's an inetd server. the echo service and the daytime service are typically internal services. Then there's also external services, services that can be dynamically forked and execed or created on demand. So things like HTTP daemons are typically forked on demand. FTP, Telnet, they're secure, SSH equivalent versions of these kinds of things. These are processes that are spawned on demand by the super server. It listens on all these ports and spawns them when requests come in. So that's often called a port manager or a port listener or a super server. You can take a look here at this link for more information about inetd. It's a very cool capability. Another feature, another thing, is something that's called the Corba implementation repository. And so this is a very cool feature that makes it possible to write application code where the client has no earthly idea where the service actually runs. All it knows is it gets an object reference, which is basically a URL on steroids, and it invokes an operation on that object reference. And that ends up going and talking to this thing called the implementation repository, which is basically a super server. And that guy keeps track of everybody who's registered using an activation table. And it checks to see whether or not there's a server running to handle this. And if not, it starts it. And then the server passes back an address, which is called an object reference, which is, again, like a URL on steroids. And that gets back to the client, and it's cached away internal to the client. And the call is actually redirected, so it ends up going over to the actual server, the one that was launched on demand. That does its thing and then sends the result back. Any subsequent call to that service is directly routed to the server without going through the implementation repository. So Corba has this really cool mechanism that optimizes things, so the first time you use it, it figures out where the correct implementation resides, launching it if necessary, and then redirects the client henceforth to go there without having to make a trip through the service, the implementation repository each time. And then, of course, the last piece of the puzzle that we already talked about is Android's Activity Manager service. So as you can see here, that works by bind service, which goes ahead and checks out the service map that's run internal, which we'll look at next time. And it starts the service by calling process.start, giving it all the information it needs to load itself. It starts up, loads in the various components it needs and the entry point and so on to its activity and its service, and away it goes. The lifecycle methods get called back, et cetera, et cetera. And then the calls you make get dispatched as appropriate there. So to summarize Activator, it basically allows you to free the clients from the responsibility of activating the resources themselves. They don't have to worry about that. They just say bind service, or they just make a call and everything happens under the hood. And it makes it look to them as if the resources were always available. Now, how many people here have taken the operating systems course here? Okay, so a few of you. So do you remember the concept of virtual memory that we talked about? Hopefully you talked about it in the operating systems course. Depends who taught it, of course. But depending who taught it, you hopefully learned something about virtual memory. So virtual memory is this concept that says, I'm going to give the processor an address, and I'm going to pretend like there's a really large address space. Now think about how big the address spaces are today with 64-bit processors, right? They're huge. But I'm actually not going to have that much main memory. Even though there's a lot of memory you can have nowadays, I'm not actually going to have, whatever 2 to the 64 minus 1 memory range is. I might have 8 gigabytes or something like that. So what you're doing is, as the processor runs, it takes a virtual address and it translates that into a physical address, and through a bunch of low-level hardware magic, it goes and it checks to see if that particular address is currently in physical memory. And if it is, you run out of the memory, you're fine. I mean, you run in that memory. If it's not there, then what happens? There's a fancy name for something that happens when you look for something in the virtual memory system and it's not found. This is very depressing to think about what you didn't learn in the operating systems course. So what happens is you incur what's known as a page fault. And a page fault basically goes out to secondary storage, like the disk, or some special battery backed up RAM or whatever, and it reads in that page in memory, stores it into the main memory, fiddles around with the page tables, and then it goes ahead and gives you back something that is actually that real place to run, and it's brought it in on demand. So virtual memory is an example of the activator pattern in a sense. It's a lower level, more systems-y concept of basically on-demand activation or lazy acquisition of resources. You only acquire something when you actually need it. Way back in the day, way back before we had ATM cards and overdraft protection and stuff like that, if you were a student at college and you wanted to get money, you would go to the local student center and you would write them a check. And invariably, the check you were writing was probably for an account that didn't have enough money in it. But back in those days, that was okay because it took a few days for the check to clear. So what you would do is, this is the activator pattern, same idea. You'd write a check, give it to the student union, they'd give you back, $50 or whatever it was. Then you'd rush back to your dorm and call your folks, and you'd say, deposit money in my account, in the next 24 hours. And assuming that they were happy with you and your grades, they would deposit the money in the account, and voila, the check would clear, everything was happy. So that was a good example of doing things on demand, right? You didn't actually have money in your account when you wrote the check, but it gave you back you got something back that looked like you had the check, and by the time the check actually cleared, the resources were there to manage it. Activator also can be used to ensure that activating and reactivating a resource will incur minimal overhead, which is very important. You don't want to have to do a lot of work to reactivate stuff. So you might, for example, have the activator pre-cache state for you. Activators could do other things too. It depends on how fancy and sophisticated you want to make them. Activators could actually take part in some kind of replicated cluster or cache management system. Or it could load balance. The activator might actually do load balancing for you. So you would ask the activator, start me a service. And the activator would look around and go, yeah, that guy over there, there's not much load over there. I'll redirect the request over there. And so then you would get back something that you would use, but it would actually be running on some lightly loaded resource in your particular cluster. So, and you could also pre-allocate stuff so that when things were reactivated, it was ready to go, it kept those things in a cache, and so on and so forth. And so you take a look at the pattern description, take a look at the Android documentation, and they talk a bit more about all of those various things. Okay. Any questions about the activator pattern? So you can see that pretty much everything we've talked about so far having to do with services touched on activator in one way or another, right? So when we talked about the started service, that was activator to start it up. When we talked about the intent service, again, sort of activator starting things up. When we talk about bound services, activators being used under the hood to start things up on demand. And you see that over and over again. And that's basically because Android is trying to be conservation-oriented in its utilization of resources, especially memory. And it's trying to do things as it needs to, and then get rid of those things so that you don't clog up the memory system.